we were asked to subtract the given radical expressions. In order to add or subtract radicals, we must have like radicals. Like radicals are radicals in which the radical part is exactly the same, meaning the index is the same, and so is the radicand. However, before we identify like radicals, we must simplify each radical completely. For the first example, we have 3 times the square root of 12 minus the square root of 48. The first step is to simplify the square root of 12 and the square root of 48 by identifying any perfect square factors of 12 and 48. We will do this by looking at the prime factorization of both radicands. So we have 3 times the square root of, the prime factorization of 12 is 2 times 2 times 3. Notice how this shows 12 contains the perfect square factor of 2 times 2, or 2 squared. So this will simplify. And then we have minus the square root of 48. The prime factorization of 48 is 2 times 2 times 2 times 2 times 3. Notice how this shows 48 contains the perfect square factor of 2 times 2, or 2 squared here, as well as here. Now if we did recognize that 48 is equal to 16 times 3, we could also write 48 as 4 times 4 times 3, which shows 4 squared is a perfect square factor of 48. Before we simplify, let's rewrite both of these using exponents. This is equal to 3 times the square root of 2 squared times 3, and then we have minus the square root of 2 squared times 2 squared times 3. And now we will simplify. The square root of 2 squared simplifies perfectly to 1 factor of 2. Because we already have a factor of 3 here, we multiply the 3 and the 2, which is equal to 6. This simplifies to 6 times the square root of 3 minus the square root of 2 squared simplifies to a factor of 2 here and here, which means this simplifies to 2 factors of 2 outside the square root. 2 times 2 is equal to 4. This simplifies to 4 square root of 3. Now notice how both radical expressions contain a factor of the square root of 3, which means we do have 2 like radicals and can perform this subtraction. Or more formally, we have 2 like radicals because both radicals have an index of 2 and a radicand of 3. We determine this difference, just like we determine the difference of like terms. We treat the square root of 3 as if it is a variable. So 6 square root 3 minus 4 square root 3 equals 2 square root 3. And now for number 2, we have 2 times the cube root of x to the 4th y squared minus x times the cube root of xy squared. The first step is to simplify the cube roots. So looking at the cube root of x to the 4th y to the 2nd, we're looking for perfect cube factors of the radicand. So let's write x to the 4th as x cubed times x. So this is equal to 2 times the cube root of x cubed times x. Written this way, we can see here we have 3 equal factors of x. And of course we still have y squared. Y squared does not contain any perfect cube factors. And then we have minus x times the cube root of neither x or y squared has any perfect cube factors, so we leave this as xy squared. The next step is to simplify the cube root of x cubed, which simplifies perfectly to 1 factor of x. We already have a factor of 2 outside the cube root, so we multiply the 2 and the x. This is equal to 2x times the cube root of xy squared. And then we have minus x times the cube root of xy squared. Notice how the radical parts are exactly the same, and therefore these are like radicals, or more formally, these are like radicals because the index is the same, and so is the radicand. To find the difference, we first determine 2x minus x, which is 1x, or x. So we have x, then the radical part remains exactly the same. So we have x times the cube root of xy squared. Remember, when the index is even and we have any variables outside the radical with an odd exponent, we do need an absolute value, which does not apply in this case. I hope you found this helpful.